Now in this lecture we're going to start looking at the Wilcoxon signed rank test. Now the Wilcoxon signed rank test is another nonparametric test that can be used to perform hypothesis tests about a population median. The Wilcoxon signed rank test tends to have greater power than the sign test. Now the sign test is the test that we've been looking at up to this point. It's that test based on the binomial distribution. If you think back to that test and think about how we calculated the test statistic, that test statistic was called EXST, and it was basically counting the number of observations that were strictly greater than the hypothesized value of the population median. We discussed the power of the sign test, and we did that by comparing it to the power of the t-test for those situations where both tests are applicable. And we saw that the sign test has quite a bit less power than the t-test in those situations. And we talked about one of the reasons why that's the case. If you think about how we do that sign test, we take each observation and then basically dichotomize it into whether it is greater than the hypothesized value of the median or not. If it is greater than the hypothesized value of the median, we assign it that dichotomized variable a value of 1, and it's 0 otherwise. And so that new variable, it's a variable at the nominal level. And so what we're doing is we're taking our original data which is at either the interval level or the nominal level, the two highest levels of data, and we're transforming those values down into nominal level variables, which are the lowest level of variable. And as a result of that transformation from high level data down to the lowest level of data, there's a loss of information, and it's that loss of information that really causes the power of that sign test to be quite a bit lower than, say, a t-test. Now, one of the other characteristics of the sign test to take into consideration is that if we think about EXST, it's counting the number of observations that are strictly greater than the hypothesized value of the median. Each one of those observations that is greater than the median is treated exactly the same. Each of those observations carries the same exact weight. Remember that their transformed or dichotomized value is 1, and then to get EXST, all we do is add up those values. And so every transformed variable that is greater than the hypothesized value of the median is assigned a 1, and so we're just adding those numbers up. And so each one of those carries the same exact weight, and that's going to be the case regardless of whether the difference between the observation and the median is 1 unit or it's 1,000 units. So that's kind of an interesting thing to take into consideration. And we may think that the observations for which the difference between its value and the hypothesized value are larger perhaps ought to be weighted more heavily in calculating the test statistic. And if we could do something like that, that may actually give us a test that's more powerful. And that is actually done in this Wilcoxon signed rank test. So that is going to be one of the reasons why the Wilcoxon signed rank test is more powerful in general than the sign test. What we're going to find is that the transformation that we do apply to the original variables, we're taking the original variable not down to the nominal level, but to one level higher than that, the ordinal level. If we think about the ranks associated with observations, those ranks are ordinal level data themselves, and that's the level at which this test statistic is calculated. And so even though we're transforming the original data down to a lower level, from interval or ratio level down to the ordinal level, we're not losing as much information because we're not taking it all the way down to the nominal level. And so there's less of a loss of information, and therefore we retain more power. Now, one of the differences between the Wilcoxon signed rank test and the sign test, you'll remember that the sign test makes no assumption, it has no built-in assumption about the shape of the distribution from which we're sampling, right? So there's no assumption that the distribution is symmetric or anything like that. And so the sign test is applicable really in any type of situation, regardless of the shape of the distribution. The sign test is going to be applicable if the distribution or the population is symmetric, but it's also applicable, as we saw, to those situations where the population might be skewed, maybe even highly skewed, or even in a situation where the distribution has heavy tails. So that's one of the nice things about the sign test, is that it's so broadly applicable. There are no built-in assumptions that restrict its usage when we go to apply it. Now, on the other hand, the Wilcoxon signed rank test does have a built-in assumption that limits its applicability in some ways. And that built-in assumption is that the distribution that we're sampling from is symmetric. In particular, that would imply that it's symmetric about its median. Because this test is based on, or derived on, that assumption, the Wilcoxon signed rank test may not be appropriate in some situations, and in particular, in those situations where the population being sampled is skewed. Now, when we considered the sign test, we talked about how to calculate its test statistic, and then we spent a fair amount of time developing our understanding of the sampling distribution of the test statistic under the conditions of the null hypothesis, but also how that test statistic behaves under the alternative hypothesis. Now, the Wilcoxon signed rank test, from a statistical standpoint in terms of determining its sampling distribution, is more complicated and more time-consuming to go through than the development of the sampling distribution of the sign test. And so because of that, we're not going to spend a whole lot of time developing the sampling distribution of this particular test statistic. The required information regarding its distribution, and in particular the critical points to use in performing hypothesis tests, that work has been done, and those critical points have been tabulated in a variety of books. And so what we're going to do is we're just going to take advantage of those tabled values. We're really not going to go into derivations. This is not a theory class, this is an applied class, and the prerequisites for this class are only a first semester methods class. And so I'm going to teach the material in a way that is consistent with that. And so we're not going to get into the theory in terms of developing or deriving the sampling distribution of the Wilcoxon signed rank test statistic. But we are going to talk in a fair amount of detail about how to calculate the test statistic. And then once we do that, we'll show how to use the table to identify the appropriate critical points so that we can evaluate the significance of the test statistic. Now, the other thing that we will do in this regard is we're going to look at not only an exact type of test using the table, but we're going to look at a large sample approximation to the Wilcoxon signed rank test, just as we did for the sign test. In other words, we're going to see how to utilize the central limit theorem to come up with an approximate reference distribution that we can use in performing the Wilcoxon signed rank test. Okay, so how do we calculate the Wilcoxon signed rank test? Well, the first step is to calculate the difference between each observation and the hypothesized value of the median. Now remember, the application at this point in time for the Wilcoxon signed rank test is as a hypothesis test about a population median. And so the first step in calculating the test statistic is to calculate the difference between each observation and the hypothesized value of the median. Now, if you'll think back to the sign test, we did that same thing. And then what we did was we counted the number of differences that were positive, or counted the number of observations that were strictly greater than the population median. All right, but we're going to, in calculating this Wilcoxon signed rank test, it's much more involved, as we'll see here. So once we do step one, once we've calculated the difference between each observation and the hypothesized value of the median, we calculate the absolute values of those differences. So we calculate the magnitude of those differences. And then what we're going to do is we're going to take those absolute values of the differences and we're going to create an ascending data array of those absolute differences. Now what that means is we're going to sort the absolute values of the differences in ascending order. So we have a list in ascending order of the absolute values of those differences between the observations and the hypothesized value of the median. And then we're going to rank the absolute differences. So in other words, we're going to calculate the ranks of the absolute values of the differences according to their position in the ascending data array. So the first one in the array is going to have rank 1, the second one's going to have rank 2, and so forth. Now, it may be the case that certain absolute values have the same value. So for absolute values that are equal, what we're going to do is assign to each one of those a common average rank, which is equal to the arithmetic mean of their positions in the data array. Now we'll see some examples of that here in just a bit. Okay, once we've assigned the ranks to the absolute values of the differences, then we're going to assign or attach to each rank the sign, the plus or minus of the associated difference. So we can think of just connecting that sign in some way to the rank. We could multiply the ranks by the sign or just keep track, associate with the sign. Okay, once we've done that, then we calculate the sum of the positive ranks and or the sum of the negative ranks, whichever one is easier. And so I'm going to denote the sum of the positive ranks by T plus, as indicated here. And I'm going to denote the sum of the negative ranks, T minus. Now, when we talk about the sum of the ranks, for example, the ranks that have negative signs attached to them, we're actually calculating the sum of the absolute values. Right? So both of these are going to be non-negative. For example, T minus here, we're not adding up negative values. So that's a potential confusing point here, all right, but I just want to point that out. You'll see when we do the example. Now, it turns out that we only need to calculate one of these, T plus or T minus, because their sum is always going to be equal to the value n times n plus 1 over 2, where n is the sample size. And so once we calculate one of either T minus or T plus, we can get the other by subtraction. So if it's easier to calculate T plus in a given situation, then once we have that, we can subtract that from n times n plus 1 over 2 and get T minus. Or vice versa. If it's easier in a situation to get T minus, we can subtract that from n times n plus 1 over 2 to get T plus. Now, once we have T minus and T plus, then we use those to calculate the test statistic. And how we calculate the test statistic depends on the type of test. So we're going to be looking at the same three kinds of tests that we looked at in the past: a right-tailed test, a left-tailed test, and a two-tailed test. Now, just let me say here that depending upon which resource you look at, book, online, whatever, they're going to explain or express the test statistic potentially in different ways. And this is driven by the type of table that they have in that resource for assessing the significance of the test statistic. Now, the particular table that we're going to use is constructed in such a way the rejection regions are always left-tailed rejection regions. In other books, the way that they've constructed the tails, they may have tables where the rejection regions are all right-tailed rejection regions. So the way that test statistics are defined and then utilized in different books, in different examples and things like that, really are driven by the structure of the table that they use. So we'll see an example of the table in just a minute, but I just wanted to let you know that if you happen to look at a different book or something like that, then they may define the test statistic a little bit differently. But having said that, if we are performing a right-tailed test, then because of the way our table is structured, the test statistic T, we're going to set that equal to T minus. Now remember, T minus was constructed back here, all right? So as we go through this process, we're going to calculate both T minus and T plus. And so if we're performing a right-tailed test, then our ultimate test statistic T, we're going to set that equal to T minus. If we're performing a left-tailed test, then we're going to set T equal to T plus. And then for a two-tailed test, we're going to set T equal to the minimum of T minus and T plus. Now, for small samples, the provided Wilcoxon signed rank reference distribution can be used to find the appropriate critical point for a given test. And like I was saying before, because of the way table 8.9 is constructed, the critical regions for the three kinds of tests that we've just described, right-tailed, left-tailed, and two-tailed, are all specified using left-tailed critical regions. Now, the reason that they've constructed it this way, and the reason that other books, for example, might have just a right-tailed type of table, is because there are symmetries involved, number one, that allow you to do that. And the other thing is that they're just fairly cumbersome to compute, so it reduces computational demands. Okay, so let's look at the three kinds of hypothesis tests. So we'll start off with a right-tailed test. The null hypothesis is going to be that the distribution is symmetrically distributed around its median cap m, which is less than or equal to the hypothesized value m sub 0. Against the alternative hypothesis, which says that the distribution is symmetrically distributed about cap m being greater than cap m sub 0. Now, I'm including this language here, the distribution is symmetrically distributed about a particular value, to emphasize and to reiterate the fact that this test is based on an assumption that the population that we're sampling from is symmetrically distributed. All right, so this is a right-tailed test in the sense that the inequality in the alternative hypothesis points to the right. Then the rejection criterion is to reject the null hypothesis if the test statistic t, which again is this t minus value, if that is less than c sub a. Now, what is c sub a? C sub a is a critical point, all right, that gives us a significance level of alpha. All right, so actually c sub alpha there. And in particular, c sub alpha is the lower alpha percentage point of the Wilcoxon signed rank reference distribution. Now, when you look up a critical point from this table, if we're doing this right-tailed test, now remember this is a one-tailed test or one-sided test, so you need to be sure to use the one-sided alpha column. And we'll see an example of that in a second, but there are columns for one-sided tests and for two-sided tests. Okay, now for a left-tailed test, all right, so the null hypothesis here would be that the distribution is symmetrically distributed about its median, which is greater than or equal to cap m sub 0, against the alternative that it's symmetrically distributed about a value that is less than m sub 0. Now, for this situation, we're going to again reject for a small value of t, but now in this case, t is not t minus, but t is t plus. So I hope that's not too confusing, but we're going to reject the null hypothesis and conclude that the alternative is true if t plus is less than, again, c sub alpha. All right, so again, c sub alpha is the lower alpha percentage point of the Wilcoxon signed rank reference distribution. And again, because this is also a one-sided test, we need to make sure that we use the one-sided alpha column. All right, and then finally for a two-tailed test, the null hypothesis is that the distribution is symmetrically distributed about a value cap m sub 0 against the alternative that it's symmetrically distributed about some other value not equal to cap m sub 0. In this case, the test statistic is the minimum of t minus and t plus, and the rejection criteria is to reject the null hypothesis if t is less than, again, c sub alpha. But in this case, we're going to use the two-sided alpha column. So this is the general way of expressing the hypotheses and the rejection criteria for these three kinds of tests. So let's take a look at an example. So suppose that a random sample of size n equal to 16 is selected from a symmetric distribution with unknown median cap m. The Wilcoxon signed rank test is to be used to test the hypotheses, the null hypothesis being that the population median is less than or equal to some specified value, cap m sub 0, against the alternative that says that the population median is greater than cap m sub 0. Now, at a significance level of alpha equal to 0.05, the rejection criteria obtained from the table calls for rejection of the null hypothesis if t minus is less than 36. Now, if you haven't already done so, open up the table A9, Wilcoxon signed rank test reference distribution, and take a look at the table. And make sure that you can identify this. In fact, here, let me go ahead and open this up here. Now, by the way, because this is a right-tailed test, all right, our test statistic t is, we're setting that equal to t minus. All right, now we're performing a one-tailed test based on 16 observations at a significance level of alpha equal to 0.05. Here is what this table looks like. This is a screenshot of part of the table. So we're dealing with a sample size of 16. We're performing a one-tailed test or a one-sided test using a significance level of 0.05. And so the critical point is 36. And so we would reject the null hypothesis if the test statistic t minus is less than 36. Now, what if we are performing a left-tailed test? So in this case, a random sample of size 18 observations is selected from a symmetric distribution with unknown median cap m. The Wilcoxon signed rank test is to be used to test the hypothesis. that cap n is greater than or equal to the specified value cap m sub 0 against the alternative that says that cap m is less than cap m sub 0. Now, we're performing a left-tailed test using a sample of size 18, and the significance level in this case is 0.01. All right, so here is the column of values that we're looking at, the sample size corresponding to n equal to 18 observations. We're performing a one-sided test, and the significance level is 0.01. And so the critical point is 33. And so we're going to reject the null hypothesis if our test statistic t plus is less than 33. All right, and then finally, let's suppose we're doing a two-tailed test. We're going to base the test on a random sample of size 12, and we're going to use a 0.02 level of significance. All right, so for 12 observations, we're looking at this column of values here. We're performing a two-sided test at a significance level of 0.02, and so our critical point is 10. And so we're going to reject the null hypothesis if our test statistic t, which in this case is the minimum of t minus and t plus, if that value is strictly less than 10. All right, now let's look at the large sample approximate test based on the Wilcoxon signed rank test. So for larger samples, a normal approximation to the sampling distribution, the test statistic t can be used. In these large sample tests, we're going to be working with t plus. Under the conditions of the null hypothesis, the mean and variance of t plus are as follows. So if the null hypothesis is true, then the mean of the sampling distribution of t plus is n times n plus 1 over 4, and the variance of t plus is n times n plus 1 times 2n plus 1 over 24. Now, we're certainly not going to derive that in this class, but we'll just take these as given. We can invoke the central limit theorem using those values for the mean and variance of the sampling distribution of t plus. And so let's suppose that we are performing a right-tailed test using the Wilcoxon signed rank test. The alternative hypothesis, because this is a right-tailed test, it's saying that the median of the distribution is greater than the specified value cap m sub 0. Then the test statistic, which we'll call zcalc, is going to be equal to the value of t plus minus the mean of its sampling distribution under the null hypothesis. So n times, and that should be an n plus 1 right there. Okay, so I fixed that. So we see here that the test statistic zcalc is t plus minus n times n plus 1 over 4 divided by its standard error under the conditions of the null hypothesis. Now the rejection criteria, if we're performing this test at a significance level of alpha, then the rejection criteria is to reject the null hypothesis if zcalc is greater than z sub alpha, which is the upper alpha percentage point of a standard normal distribution. And then finally, to calculate the p-value, the p-value will be equal to the probability that a standard normal random variable z is greater than or equal to the observed value of zcalc. So this is little zcalc. All right, so whatever that observed value is, the probability that the standard normal random variable is greater than or equal to that value, that is the p-value. Okay, for a left-tailed test, things are similar. All right, we see here that we've got a left-tailed test. In the alternative, we're saying that cap m is less than the specified value. We calculate zcalc in exactly the same way. T plus minus its mean under the conditions of the null hypothesis, which is n times n plus 1 over 4, divided by its standard error. In this case, we're going to reject for small values of zcalc. If zcalc is less than negative z sub alpha, where again z sub alpha is the upper alpha percentage point of the standard normal distribution. And then the p-value for the test is the probability that the standard normal random variable is less than or equal to the observed value of zcalc. And then finally, the approximate two-tailed test. We again calculate the test statistic in exactly the same way, but now we're going to reject the null hypothesis if zcalc is either small or if it's really big. All right, so we're going to reject the null hypothesis if zcalc is less than negative z sub alpha over 2, or if it's greater than positive z sub alpha over 2. And then finally, to calculate the p-value, that will be equal to twice the probability that the standard normal random variable is greater than or equal to the absolute value of the observed value of our test statistic. Okay, so that's how we perform the Wilcoxon signed rank test, both the exact test using the table and the approximate test using the standard normal distribution. Now let's look at some examples. So a random sample of n equal to 20 households was surveyed in a certain area, and the total income for each household was obtained. The data are given in the table below. The question of interest is whether there is sufficient evidence at the 0.01 level of significance to conclude that the median household income for the area is different than $13,000. We're going to use the Wilcoxon signed rank test to answer this question. So here are the data that we're going to be using, and these are data in thousands, obviously. The purpose is to determine whether we can conclude that the median household for the area is different than 13,000. So this is going to be a two-sided test. So the null hypothesis will be that the distribution of incomes is symmetric about 13. The alternative is that the distribution of incomes is symmetric about some other value, so cap m is not equal to 13. Now, because this is a two-sided test, the test statistic is going to be the minimum of t minus and t plus. Now, the rejection criteria, we're going to reject the null hypothesis if our test statistic is less than what value? All right, so here's where we need to go to the table. And so we have a sample size of 20. We're performing a two-sided test, and we want to perform that test at a significance level of 0.01. And so the critical point for the test is going to be 37. And so we're going to reject the null hypothesis if t is less than 37. All right, so now let's calculate the test statistic. All right, so I've got my data listed in this spreadsheet, observations 1 through 20, okay, 17.1, 12.1, and so forth, down to the last one, 16.6. And then what I'm going to do is I'm going to, the first step, I'm going to take the difference between each of these observations, each of these values, and the hypothesized value of the population median, which was 13. All right, so I get a list of these differences. You can see some are positive, in fact most are positive, but some are negative. What we do in the next step, and it may be kind of hard to see here, but there's an absolute value in this column. There's absolute value around income minus 13. So we're going to take the absolute value of these differences. Okay, and so see here we have all positive values, right? These are the magnitudes of the differences. All right, now the next step, I'm going to sort this spreadsheet, for now at least, based on these absolute differences in ascending order. So I'm creating a sorted data array based on this column of values here. So that is in the next slide. All right, and so you can see here that I've sorted these things in ascending order. Then the next step is to assign a rank to each one of these absolute differences based on its position in the sorted data array. So this value is in the first position, and so it's going to get rank 1. Now notice that the next two absolute differences are the same. They're both 0.2. And so each of those is going to get a rank that is equal to the average of what the ranks would be if they were not identical. So these are in positions 2 and 3. And so each of these is going to get a rank of 2.5. And then you'll see that we have the same issue down here. 0.3 is repeated, okay, in 1, 2, 3, 4, the 4th and 5th positions, all right? So each of those will get a rank of 4.5. And so that is how we assign the ranks. Now notice that after we get beyond this point, we don't have any identical values, and so they get the rank according to the row that they're in. Once we calculate the unsigned ranks, then we're going to calculate the signed ranks. And what we're doing here is we are attaching the sign associated with this original difference to the unsigned rank. So this is a positive value, so the signed rank here is positive. This is a positive value, and so signed rank is positive. But now this difference is negative, all right, and so the signed rank associated with 2.5 is negative, and so forth. All right, once we have that, once we've identified the positive and the negative ranks, then what I'm doing is just transferring over into these two columns. It's just an easier computational way to do this in this spreadsheet to calculate T minus and T plus. So I've just got a little bit of conditional logic here in these cells. If the value is negative, then I'm going to put its positive value here, and if the signed rank is positive, then it just gets that value in this last column. And then we calculate the column total for each of these columns. And so what this tells us is that T minus, the sum of the negative ranks, is 23, and T plus, the sum of the positive ranks, is 187. Now notice that the sum of those values, 23 plus 187, is 210, which is in fact n times n plus 1 over 2, 20 times 21 over 2. Now, the way that I've calculated this, I don't need to use the relationship that I showed you to calculate one after I've gotten the other. It's just as easy to calculate it this way using the spreadsheet, but we can use that relationship just to check our work here and make sure we've got the spreadsheet constructed correctly. All right, and then if I wanted to, I could resort the spreadsheet, again based on observation number, but there's absolutely no reason to do that. Once we have these values, that's all we need from the data set. And so now the conclusion is, remember that in this case, the test statistic, because this is a right-tailed test, the test statistic is T minus. All right, so T is equal to 23. And because that's less than our critical value of 37, we reject the null hypothesis and conclude that the alternative hypothesis is true. And so we can say that there is sufficient evidence at the 0.01 level of significance to conclude that the median household income in this area is different than 13,000. Okay, so that's how we would perform the exact test using the Wilcoxon signed rank test. Now let's take a look at how to do the approximate test. Even though this is not a really large sample, at least we can see the mechanics of how to do this. And so again, the null hypothesis is that the distribution of incomes is symmetric about 13. The alternative is that the distribution is symmetric about some other value. The test statistic is zcalc equal to T plus minus n times n plus 1 over 4 divided by the square root of n times n plus 1 times 2n plus 1 over 24. All right, so again, this n times n plus 1 over 4 is the mean of the sampling distribution of T plus under the conditions of the null hypothesis. And this value in the denominator, the square root of all that, that is the standard deviation of the sampling distribution of T plus under the conditions of that null hypothesis. Now, this is a two-tailed test or a two-sided test at a significance level of 0.01. And so we are going to reject the null hypothesis if zcalc is either less than negative z sub 0.005, which is negative 2.575, or if zcalc is greater than positive z sub 0.005, which is positive 2.575. Calculation of the test statistic. All right, so we're going to plug in the value of T plus, all right, 187, and we calculate these other quantities, all right, and that turns out to be a test statistic equal to 3.06. All right, and so we could say that since 3.06 is greater than 2.575, we reject the null hypothesis and conclude that the alternative hypothesis is true. Now, I've also included, as I am doing in all these examples, just for completeness' sake, showing how to calculate the value of the p-value. All right, so the p-value in this case, because this is a two-sided test, is equal to 2 times the probability that the standard normal random variable z is greater than or equal to the absolute value of our test statistic, which is 3.06. And using the standard normal table, I find that that probability is 0.00111, and then I multiply that by 2, and so the p-value is 0.00222. So I could also conclude, since the p-value is less than or equal to 0.01, conclude that the null hypothesis is false and that the alternative is true. So we can do it either way, using the test statistic and critical point method, or using the p-value method. All right, and so using this approximate test, we're going to draw the same qualitative conclusion. There is sufficient evidence at the 0.01 level of significance to conclude that the median household income in this area is different than $13,000. Now, what if instead of a two-tailed test, Suppose the question of interest was whether there is sufficient evidence at the 0.01 level of significance to conclude that the median household income for the area is greater than $13,000. So it's a one-tailed test. What would the conclusion be there? Well, let's check this out. So we've got the same data. All right, so in this case, the null hypothesis is that the median is less than or equal to 13 against the alternative that it's strictly greater than 13. In this case, the test statistic is T minus. It's a right-tailed test, and so the test statistic is T minus. And so the rejection criteria is to reject the null hypothesis if the test statistic T minus is less than the appropriate critical point determined from table A9. All right, and so let's take a look. Okay, so again, we've got a sample size of 20. We're performing a one-sided test in this case at a significance level of 0.01. And so now, for this test, the critical point is 43. And so the rejection criterion is to reject the null hypothesis if the test statistic T minus is less than 43. Now, we saw previously, we calculated both T minus and T plus. T minus was 23, T plus was 187. And so since the test statistic is equal to 23, which is less than 43, we reject the null hypothesis and conclude that the alternative hypothesis is true. So in this case, there is sufficient evidence at the 0.01 level of significance to conclude that the median household income in this area is greater than $13,000. Now let's do the approximate test for this situation. So again, we have the hypotheses here. The test statistic is the same test statistic, again calculated in terms of T plus. And since this is a right-tailed test, we're going to reject the null hypothesis if z-calc is large, and in particular if it's greater than the upper first percentage point of the standard normal distribution, and that z-value is 2.33. So again, we calculate the value of the test statistic. It's exactly the same as it was before, 3.06. And again, we can calculate the p-value. Because this is a right-tailed test, the p-value is just the probability that the standard normal random variable is greater than or equal to 3.06. And from the standard normal table, that probability is 0.00111. And so using either the test statistic and the critical point approach or the p-value approach, we draw the same conclusion. Since 3.06 is greater than 2.33, or equivalently, since the p-value is less than or equal to 0.01, we reject the null hypothesis and conclude that the alternative hypothesis is true. And so we can say that there is sufficient evidence at the 0.01 level of significance to conclude that the median household income in this area is greater than $13,000. Okay, so this is how you do the Wilcoxon signed rank test. And what you would find in practice is that the Wilcoxon signed rank test tends to have quite a bit more power than the sign test. And in fact, in some cases, the Wilcoxon signed rank test can have power approaching that of a t-test. So it's a very useful alternative in those situations where it is applicable. Now, I will say that, and remind you, that it does have this built-in assumption that the distribution that we're sampling from is symmetric. So that becomes a limitation on the situations to which it can be applied. If the distribution that we're talking about is not symmetric, then this test may not be applicable, may not be appropriate. And in fact, in this very example, this may be a situation where the Wilcoxon signed rank test may not be applicable. If we think about home prices, and if we think about the distribution of home prices, do we consider that distribution to be symmetric about its median? Or might we expect it or suspect it to be potentially skewed to the right? And if we think about that, and actually, if we go back and look at the original data, all right, so let me scroll back here, all right, and find that original data set. Notice that most of these values are in the range from between around 10 up to 20, but we do have one value that's way up there at 93.4. All right, so that might tell us or lead us to conclude that the distribution has actually got some skewness to the right. And it may give us pause in considering the Wilcoxon signed rank test to be appropriate here. But you see how it works. And it is a little bit more involved in terms of doing the calculations. You know, we have to do table lookups. and so forth. And the derivation of the sampling distribution of the test statistic is more involved, and so we're not going to go into that. All right, but you do see the mechanics of how this is done. Now, in the next few videos, we're going to revisit both the sign test and the Wilcoxon signed rank test, and we're going to look at how to apply these tests in another situation. In fact, it's probably an even more useful situation than what we've looked at up to this point. Up to this point, we've been using both the sign test and the Wilcoxon signed rank test to test hypotheses about the median of a population. But now what we're going to do, we're going to find that we can apply these two tests, these same two tests, in a situation where we want to compare two distributions or compare two populations using paired samples. Now, that should ring a bell. If you think back to your first methods class, one of the hypothesis testing situations you looked at was comparing two population means using paired data. So this is the same kind of situation. But instead of framing the hypotheses in terms of population means, we're going to frame them just in terms of the distributions in general. And so the null hypothesis will be that the two populations are the same against the alternative that they're different, and in particular, we'll be looking for a difference in location. And what we're going to find is that both the sign test and the Wilcoxon signed rank test are useful. They can be used in those situations. And in fact, the limitation that the Wilcoxon signed rank test has, because of that assumption of symmetry, really is not an issue in this other situation where we're looking at paired samples and comparing the two populations. So that's going to be the topic of the next one or two lectures. We've finished up what we're going to talk about here. We will continue on in the next video.